Welcome learners. In today's lecture, we are going to talk about Thevenin and Norton equivalents. So we want to know what are these equivalents and why they are necessary when dealing with circuit analysis. So the reason we use them is at times in circuit analysis, we just want to focus on what happens at the specific terminals of any electronic device. For example, if you have any electronic device at home, let's say you have a microwave oven and you want to know that what happens when you connect that to a power socket. Let's say you are getting 230 or from 220 to 240 volts in your region. So this is the power socket, a 3-port connection, and you are interested only to find what happens when you put the plug of the microwave inside this socket. So we are not interested what is happening in terms of voltages and currents inside the microwave components. We are only interested in its terminal characteristics. By terminal, I mean what happens when you put the plug of the microwave inside this power socket where the main voltage source is coming from the grid station. And this is now the terminal analysis with regards to the microwave oven. So in order to do the analysis of the voltages and currents at the terminal, we need to use techniques which are based on Thevenin and Norton equivalents. And we come to this understanding that whatever is the voltage and current being received at the terminal, it is equally distributed among all the components. So basically we want to know what is happening, or we understand this, that the voltage and current received at the terminals is going to be equally distributed among all the components inside the microwave or all the elements or instruments that are using in your household. And this is where the Thevenin and Norton equivalent is beneficial to us. So let us see what happens with Thevenin equivalent. So Thevenin equivalent, as I mentioned, focuses on the terminal behavior of any device, and it aids us in analyzing electrical circuits. So how this works? So let us assume that you have an interconnection of, or you have multiple sources plus loads. It's a complex network and it is basically connected to through a two-terminal device. So this is the condition, that it should be a two-terminal device. These terminals are basically the electrical wires. So how can we represent these multiple sources and multiple loads? In order to do this, the Thevenin says that you translate or you represent these multiple sources with just a single voltage source. We call this as V Thevenin. And with a single resistor, we call this as R Thevenin, and then we have the terminal behavior or connected with any two electrical wires, AB. So all the sources and loads are now just represented by two variables under the Thevenin equivalent, which is V Thevenin and R Thevenin. So the behavior of all the voltages and resistance are represented by these two values, and this is what Thevenin equivalent is. And we believe that all these values will be equally contributed to whatever was the number of elements inside this original circuit. Similarly, if we talk about the Norton equivalent also gives us a sense of same currents and resistors for any kinds of or multitudes of sources and loads. In order to represent this Norton, we basically represent all these sources. So again, we have arbitrary sets of sources plus any elements, electric elements represented by or connected to any two electrical wires. We call these as terminals. So these loads can be represented by a single current source connected to a single resistor, and again we have these terminal values A and B. So this will be the R Thevenin, the same resistor, and this will be the Norton current, which represents or gives us the sense of all the elements being utilized in this complex network. So we can find then the current or Norton equivalent by the ratio of V Thevenin to R Thevenin. So these are the two ways where we can use the Thevenin equivalent. So this is the representation of the Thevenin equivalent model, and the Norton equivalent, this is the Norton equivalent representation to simplify a complex network of loads and sources. And if you look at these are basically the same kind of representations which we saw in our previous lecture of source transformations, where we converted from a voltage source to a current source and vice versa. So now let us look at some of the examples to better understand how these equivalents are formulated and how the circuit is analyzed. So if we want to find the Thevenin equivalent, so let us say if we want to find the Thevenin equivalent, so the idea is very simple. Whatever is the complex circuit, let us say A, and these are the terminals, we basically convert that complex circuit into a connection of V Thevenin to a single resistor R Thevenin, and then this is point AB. So basically this portion gets converted into this portions and terminal remains the same. Now in order to find this V Thevenin and R Thevenin, we consider a criteria. We say that if you want to find the V Thevenin, we have to assume that whatever is the load we connect to this terminal, let's say we connect a load RL, it has to be an open circuit connection, which means that the resistance is very high. Since the resistance is very high, we know that the voltage appears across this. So in order to find V Thevenin, we assume that the load connected is an open circuit load. And when you want to find the R Thevenin, we are going to consider the load to be a short circuit, which means there is no resistance. So the current can easily flow through this. So these are the two principles that we utilize in solving the or finding the V Thevenin and R Thevenin of any given electrical circuit. So let us look at an example and see how we can better understand this. So for example, I have this circuit. I have a voltage source of 25 volts connected to a 5 ohm resistor and a 20 ohm resistor. Then I have another current source of 3 amps. Then I have a 4 ohm resistor, and then these are the terminals A and B. And I have been asked to find the Thevenin equivalent for this circuit. Find the Thevenin equivalent of this circuit given. Okay, let us now solve this. So how we are going to begin? We know that if we want to find the Thevenin equivalent, we need to find two scenarios. We need to first find the V Thevenin and then we need to find the R Thevenin. So let us first start with the V Thevenin. So in order to find V Thevenin, we know that we have to consider that this circuit or terminal or the load applied to this will be an open circuit. So this is VAB, which is basically our V Thevenin, and since the voltage is parallel, so we need to find the voltage appearing across this 3 amps source. So this is where we need to find this V1. Once we know V1, this is going to be V Thevenin because this is equal to the voltage or the open circuit voltage at the terminals. So VAB, the open circuit voltage, is going to be V1, and obviously when we find this, we are going to call this as V Thevenin. Now there are different ways to find the voltage appearing across 3 amps source. Either we can use KVL, KCL, we can also use source transformation, we can use mesh currents, we can use node voltage method. Since we need to find voltage, let us use the node voltage method. So let us use the node voltage method. We can also solve this using the source transformation to find the voltage V1. Once we know the voltage V1, we know the voltage here and here is parallel, so it will be the same voltage that will appear here, which is VAB, and this is what we need as V Thevenin. So for node voltage, we first need to know how many essential nodes are there, NE. And once we know the essential nodes, we can figure out the total number of equations. So if we look around our circuit, we come to this point, we can see we have 1, 2, 3 nodes. Okay, this can become an essential branch, we can connect 4, but after that we also have a single element. So so instead we take this, why not we just focus on this point and take this to be our essential node. So if this is our essential node, it is going to connect 25, 5, 20, the current source and 4 ohm, and then we need to take another common node which is the ground. Let us take this to be a ground. So we have only, so the equation is now we have only two essential nodes. So 2 minus 1, this means we'll have only one equation. So let us now write the equation. So we know that the second method after figuring out the essential node is to imaginary or say the hypothesis that the currents are leaving this node, and then we write the equations or the currents equation for this. So the equation will be V1 minus 25 divided by 5 plus V1 divided by 20 minus 3 amps, and we don't need to consider this current moving towards the right of the, because this is an open path, so there is nowhere for the current to move because current in this path is 0. Since the current is 0, there is going to be no voltage drop across the 4 ohm. This means the equation will not be written for the current on the right hand side of this essential node V1. So the equation comes out to be equal to 0, and if you solve this, the voltage comes out to be 32 volts. So since this is the voltage which is across the 3 amps, we know that this 32 volt voltage is basically the voltage that will appear across the terminals VAB, and this is our Thevenin voltage which is 32 volts. So we have easily figured out what is the Thevenin voltage. Now the next step is to find R Thevenin. So there are two ways or two methods to find the R Thevenin. We first look at the first method. So method number 1 is that we redraw the circuit. So this is the voltage source, 5 ohm, 20 ohm, the current source, then we have 4 ohm, and then we have the terminals A and B. So this is 3 amps, this is 4 ohm, this is 20 ohm, this is 5 ohm, and this is 24 volts. So the first method is that we are going to draw the circuit again, and now we know by principle that in order to find R Thevenin we have to make a short circuit or where the resistance is 0. So we are going to connect a short circuit or a wire at terminals A and B, and we call this I of SC. SC stands for short circuit. Now once we have this now what we can do is again we apply the node voltage method, and let us call this as V2 and see the flow of currents from all these points. So it will be V2 minus 25 divided by 5. Why we are finding V2? Because this IS depends upon V by R, right? So once we know this V or V2, we can find the R Thevenin which is the required. So V2 minus 25 divided by 5 plus V2 by 20 minus 3. This time we are going to write the equation for the current leaving because the path for the current is now defined. So it is going to be V2 by 4 equals to 0. And once you solve this, V2 comes out to be 16 volts. Once we have 16 volts, the short circuit current comes out to be 16 divided by 4, which is equal to 4 amps. Now once we have the 4 amps, so R Thevenin is going to be V Thevenin divided by the short circuit current, and V Thevenin was 32 volts. This is 4 amps, and the final resistance comes out to be 8 ohm. So now we have figured out what is R Thevenin as well. So our simplified circuit now will appear something like this. This whole circuit, the one that we had over here, this whole portion, so let me draw it with a different marker. So this whole circuit over here is now transformed into something, a simplified form of a single voltage source connected with a single resistor. So this is A, this is B, this comes out to be 32 volts, and this is 8 ohm, and that's it. So we have simplified our circuit, or we have basically figured out the terminal behavior of the circuit using the Thevenin equivalent. So this is how we solve the Thevenin equivalent method. Okay, as I mentioned, there are two ways to find R Thevenin, and now let us look at the second way. So this was the first method. What is the second method? The second method is the shortest or shortcut method or deactivation method. Deactivation method. To find what? To find R Thevenin. So if you are not interested in applying the node voltage method to the circuit over here, what we can do is we can deactivate certain independent sources. So what does it mean by deactivation? Let us say I have the same circuit, (5 ohm, 20 ohm, 25 volts, and then I have the current source of 3 amps, and then I have a 4 ohm, and then we have the terminals A and B, and this is VAB that we had. Okay, and let us say I want to figure out how to find R Thevenin without applying the node voltage method as we saw previously. So in order to go about this, what we do is we use the deactivation method. Deactivation means that whenever you have, so the deactivation means whenever we have independent sources, whenever we have independent sources, not the dependent, please remember, not the dependent. Whenever we have independent sources, those sources being voltage source and current source, we make them zero. We make those sources equal to zero. How we make them zero? We know that if you want to make a voltage appear to be zero, you have to use a short circuit wire. If you want to make a current equals to zero, you have to use a open circuit connection. So this is the principle that we are going to apply on this circuit, especially on this voltage source and this current source. So how we can redraw this circuit? By deactivating the sources. So let us say if I want to find R Thevenin, so the new circuit will be the voltage source gets deactivated. I am left with 5 ohm, 20 ohm. So this is 5 ohm, 20 ohm. Then the current will become an open circuit because we want to make it zero. Then I am left with 4 ohm, and this is the terminal A and B. Now let us find the resistance seen from the terminal AB. And when we look at the terminal, it becomes very prominent that it is just an equivalent resistance kind of a problem where resistors are connected in series and parallel. So we know that if a current is flowing from here, this resistor, it will straightly come at this point. The current cannot go here because this is an open circuit. Then the current comes to this point, and here we have a distribution of current into multiple paths, which means that these two are connected in parallel. We can also verify with the combination of the pair nodes. So the resistor 20 is connected to this pair node, and resistor 5 is also connected to the same pair node. So how can we find the R resistance? So RAB or R Thevenin, let us say R Thevenin is equal to RAB, which is going to be 4 plus 5 parallel to 20, and once you solve this, it comes out to be 8 ohm as well. So you get the same answer which you got previously using the node voltage method. So this is the method number 2, which is the shortcut method or deactivation method, which we use to find the R Thevenin. Okay, now we have found the Thevenin equivalent. What do you think? How can we find the Norton equivalent of this same circuit? So you have two ways to go about it. We know that this is the R Thevenin. So either you can first find the R Thevenin of the circuit and then use source transformation to get the Norton equivalent. So if this was the R Thevenin, which we just saw, 8 ohm of R Thevenin and 32 volts of V Thevenin across terminals A, B. So if you want to find the Norton equivalent, we can use the source transformation technique where these two will be converted into a single current source connected by the same resistor in parallel, and then we have the terminals A and B as it is. So the current comes out to be V by R, which is equal to 4 amps. So this is the direct method to find the Norton equivalent by using the source transformation method. And if you don't want to go through this track, then you can again use the source transformation on the original circuit. For example, if I have the original circuit again drawn over here and I want to find the Norton equivalent of it. So let us find the Norton equivalent without going through the process of finding the Thevenin equivalent. So we have the circuit, again the 25 volt source, the 5 ohm resistance, the 20 ohm resistance, followed by the current source of 3 amps, and then you have the 4 ohm at the terminal AB. So this is 4, this is 3 amps, this is 20 ohm, this is 5, and this is 25 volts of source. Now if you want to find the Norton equivalent, what you can do is you can apply the source transformation. We know that these two are connected in series, so I can transform it into its equivalent current. So this is going to be a current source followed by the same resistor in parallel. So then the I equals to V by R, and this comes out to be 5 amps. The remaining circuit is as it is. So I have 20 ohm in parallel now. Sorry about that. I have 20 ohm in parallel now. I had this connection over here, and this is the 5 ohm, this is the 20 ohm. Now I have the current source 3 amps, then I have the 4 ohm with its terminal AB. Okay, now once I have this, I can immediately see that these two are in parallel, these two resistors, so I can find their R equivalent. So R equivalent is going to be 5 into 20 divided by 5 plus 20, which comes out to be 4 ohm. Okay, and I can also see that this current is in parallel with this 3 amps current. So we know by the sources rule that if we have two currents parallel to each other in the same direction, as it was 5 amps and 3 amps, so we can combine it into a single current source of 8 amps. So the new circuit after all these two simplification comes out to be an 8 amps current source followed by 4 ohm equivalent resistance, and then you have the 4 ohm with the terminals A and B. So this is what we get. Now again we can do the conversions. This is a current source in parallel with the resistor, so I can transform this into a voltage source again with the resistor in series, and this is terminal A and this is terminal B. So this is 4 ohm. The new value comes out to be, so this is the voltage source now 32 volts. This was the original 4 ohm. Now in series, if I add these together, I get 8 ohms in series, and now again 4 and 8 ohm can be transformed into a current source and with its terminal A and B. So this is 8, and the current comes out to be V by R, which is excuse me about that. So it is going to be V by R, and you have 4 amps of current. So this is how you solve the Norton equivalent by using the source transformation method. Okay, so now let us come to another scenario of dependent sources. So till now we have talked about how to deal with independent sources and find their Norton and Thevenin equivalent. But what about if we have a dependent source, and how we are going to solve that kind of a circuit? So let us see how the dependent source is going to be. So for this example, we have a voltage source, an independent voltage source connected with the resistor. Then we have a dependent source, and we are connected to like this. So this is a 5 volt, this is a 3 volt, this is a 2 kilo ohm, and then we have another source followed by a resistor and then we have the terminals A and B, and this is a current control source. So this is a 20I and this is 25 ohm. The current is flowing in this direction and the current is I is flowing in this direction, and we need to solve this in order to figure out the Thevenin equivalent. So we need to find the Thevenin equivalent of this circuit across terminals A and B. So let us see what do we understand by this circuit. So we have a independent source of voltage source of 5 volts. We have a dependent voltage source of 3 volts. We have a dependent current source of 20 amps, and then we have voltage appearing across the 25 ohm. So in order to find VThevenin, we need to see what is the voltage appearing across AB terminal, which is the open circuit voltage. So whatever is the voltage appearing across 25 ohm, this will be the VThevenin. So this is the voltage that we need to find by considering the open circuit connection. Now if you look at this, it's a very straightforward example to solve. As we saw previously, independent circuits, we solve the circuit section by section, and this circuit diagram shown here is the example of an amplifier. Okay, or it's a BJT, depends upon the configuration, which configuration is it. So in this circuit we can see that if you want to find the voltage across the 25 ohm resistor, we know that the current is coming and entering from the negative terminal. So I can immediately say that VThevenin is equal to I into R, and since the current is entering the negative terminal, so it is going to be negative I. So it is going to be minus 20I multiplied by 25 ohm, and it comes out to be minus 500I, and this I is basically appearing over here. This is the I where it is appearing. So what is now I? I is basically V by R, which is 5 minus 3 V divided by 2K. So this is the I that we have, and this V is again dependent upon this V, which is across the 25 ohm, and we call this as VThevenin. So this is now basically VThevenin. So just input the value of I over here. So we can say now we have two VThevenins, one is the unknown and one is the controlling. So VThevenin equals to minus 500I, which equals to minus 500, and the value of I is 5 minus 3 VThevenin divided by 2K. If we solve this, this comes out to be minus 2500 plus 1500 VThevenin divided by 2K, and if we further solve this, it comes out to be minus 1.25 plus 0.75 VThevenin, and finally VThevenin comes out to be minus 5 volts. So this is the Thevenin voltage of negative 5 volts. Now the next step in this question is to find the R Thevenin. So again, we can use both methods, but we stick to the shortcut method or the deactivation method, which is the second method. And in this method, for dependent sources, we call this as a test source method. So the idea remains the same, that whenever we have independent sources in the circuit, for finding R Thevenin, independent sources, we basically deactivate them. By deactivation, we mean we make the sources IS and VS equals to 0. But once we have a dependent source, so for the dependent source, we use a test voltage at the terminals. Test voltage at terminals. What it means, we'll shortly see. So now in order to find this R Thevenin, let us redraw the circuit. So the circuit is 5 volts followed by 2K. You have the dependent source, and then you have another dependent source followed by the resistor, and then we have the terminals A and B. And now what we do is, let's input the value 25, this is 20I, this is 3 volts, this is 2K, and this is 5 volts, and the current is moving in this direction. Okay, now in order to solve this using the second method to find the RThevenin, we are first going to deactivate the independent sources. So in this full circuit diagram, the only independent voltage is the voltage source. So we are going to make it as a short circuit, which means we are going to remove this and consider this to be a short circuit. So now this is a straight line. Okay, since we don't have any other independent sources, now let us focus to the dependent sources. How we are going to find the dependent sources? We are going to apply a test source at the terminals, which means that we are going to assume that we have connected another voltage source from the outside to this terminal. We call this V of t, and this V of t is producing a certain current I of t. And now the current is moving in this direction, it will come in this direction, it will follow this direction, it will go upward, it will also take this direction, and it is going to take this direction to complete the flow. So this is what is the test voltage. Test voltage is we basically introduce a voltage source and connect it to the terminals A, B in order to find the RThevenin. Now let us come to this point and apply the KCL on this, because now the currents are entering and leaving the system. So the current is entering and leaving this system. So we do it like this. So the KCL at this point is entering current is minus I of t, leaving current is plus 20I, and another current leaving is in terms of voltage, because we know this was voltage. So it is V divided by 25 equals to 0. So I can write it in terms of IT is equal to 20I plus Vt divided by 25. Now what is I? We know that I is basically appearing over here, and you can see it is entering into the 3 voltage source. But so I can write I is equal to V by R, because 5 volt is disappeared. So I just have 3V divided by 2K, and I'm going to take a negative sign because the direction of this current which is coming through the test voltage is opposite to the original current I. So this is going to be minus 3V divided by 2, and this V is nothing but the Thevenin voltage, which is appearing over here, V of t. So now input the value of I into this equation. So you get the value of 20 minus 3Vt divided by 2K plus Vt by 25 equals to I of t. If I simplify this, it comes out to be I of t Vt is equal to 1 divided by 100, and this basically is RThevenin, which is going to be 100 ohm. So this is the solution to this problem. So we have basically used the second method to give us the RThevenin and VThevenin. So finally the final circuit comes out to be a single voltage source connected to a resistor with terminals A and B, and this is minus 5 volts, and RThevenin is 100 volts. You can also, if you don't want to write the voltage to be a negative volt, you can just write it as plus 5 volts, but the polarities will be now like this. So this is basically the simplified or Thevenin equivalent representation of our dependent circuit shown over here. So I leave you with some more practice questions, so you can practice on this Thevenin and Norton related problems. You can also find the Norton of this dependent source over here. So a few examples for you to practice and see what is the output of these examples. So let's say practice problem number 1 is, let us say you have a voltage source and it is connected to a 5 ohm resistor, 20 ohm resistor, it is connected to a 12 ohm resistor, then you have an 8 ohm resistor, and then you have terminal A and terminal B. This is 8 ohm, this is 20 ohm, this is 5 ohm, this is 12 ohm, and the voltage source is 72 volts. You need to find the Thevenin equivalent for this. Okay, just to give you a starting point, you can apply the node voltage method, because we know that the Thevenin voltage depends upon the open circuit condition, which is over here VAB. So VAB is going to appear across this point over here. So whatever is the voltage appearing at the 20 ohm, it is going to be your Thevenin. In order to apply node voltage, you can have essential nodes at this point, and even this point, and then you have the common ground over here. So then you can figure out the voltages at essential node, let's say A, B, C, and D is a ground node. So you have basically 4 essential nodes, so you will get 3 equations, and you might come across a special case of node voltage and the equation might reduce to 2 equations. So then you can figure out what is the voltage appearing, let us say at VB. This will be the Thevenin voltage required. I'll leave you with the answer. So for the Thevenin voltage, the VT comes out to be 64 volts and R Thevenin comes out to be 6 ohm. This will be the voltage from here to here. Okay, so this is one example that you can try. You can also work with dependent sources. So let us say this is another question that you can work with. Practice problem number 2. So that is, let us say you have a voltage source and a 2 ohm resistor, then you have a current source of 4 amps, and then you have another 8 ohm resistor, and these are the terminals. So this is 8 ohm, this is 4 amps, this is 2 ohm, this is a 24 volt source, and you have a dependent source connected over here with this point over here. So this is a current controlled 3I of X, where I of X is going through the 8 ohm resistor, and you again can use the you need to find the Thevenin of this as well, Thevenin equivalent of this. Just to give you an hint, you can have this as essential node A, this as essential node B, and then you just note a grounded essential node 3. The V Thevenin and R Thevenin for this case comes out to be 8 volts and 1 ohm. So have a go at this question as well, because dependent sources based on the previous feedback of the students seems to be complicated to solve compared to the independent sources. Okay, finally coming to the last 2 topics of this chapter, and these are basically related to maximum power transfer and superposition principle. So what is maximum power transfer? Maximum power transfer. So in circuit analysis, we have been talking a lot about the power transmitted from one source to the load, or power going through different circuit elements, but we are often interested that how much total power is supplied or absorbed by the system. So there are 2 scenarios where we look into the problems or 2 scenarios where the power is maximum utilized. The first is power in terms of efficiency. In terms of efficiency, like we say how much percent, let's say 60% or 80% power is being consumed by the system, and this normally applies to high power system. Examples, or you can say utilities. For example, you have your grid station, how much power is being generated, how much power is being consumed by the load. You have your normal power generators, and if we talk about even distribution, that how much power is being distributed to the homes, to the industries. So this is basically in the context of a larger or broader power system. Whenever we talk about power in terms of percentages or efficiency, we are talking about a very huge system. But there is a second category of power analysis as well, and that deals with our communication systems. And these systems basically have very low power analysis, like from 100 of 1 watt to 5 watts. So these are the lowest power analysis that we do, because if you remember in the first chapter we talked about electrical engineering in the context of communication is the power of, or is basically the generation, transmission and measurement of small electrical signals. So we don't normally deal with high power analysis, we just see a small amount of power transferred between signals, and this is where the communication system powers fall, or in this category we fall. So in this course normally we are dealing with the second category of power or maximum power transfer or power analysis, where the values of the power wattages are low in the range of 1 to 5 watts. Now, what is the concept of maximum power transfer? So the maximum power transfer says that if we have any network of circuits or elements, so we want to know that if we connect any load to that network, how much the power is transferred from this network to this load. So we just need to figure out the mathematical expression to how much power is being transferred to this load, which is basically consuming this power. So in order to find this power being received at the load, you can see we have these terminals A and B. So this network can be solved using the Thevenin and Norton principle. Thevenin and Norton equivalent principle. So for example, if I want to know how much power is being delivered to this load R of L, let's say this is my terminal A and this is terminal B, what I can do is I can just figure out what is the behavior in terms of the Thevenin or Norton voltage. So I can find V Thevenin and I can find R Thevenin. Even I can also find the current in terms of Norton and Thevenin, and the load remains the same as it is. So it can be R Thevenin and I Norton. So these are the ways where I can figure out what is the behind the terminals, what is happening in this vicinity in the terms of Thevenin and Norton equivalent. If I apply the Thevenin equivalent, I just need to figure out what is the current. So I can say the current over here is V Thevenin divided by R Thevenin plus the load value. Now once I know the current, I can easily apply the equation of power, which is I square R of L, to know how much maximum power has been transferred to the load. So P is equal to I square RL. Just input the value, let's say V Thevenin divided by R Thevenin plus RL whole square multiplied by RL. So I will get the maximum power equation. Without going into the mathematics, let us say what is going to be the equation for this. So we take this equation and we apply the derivative in terms of the resistance. So we get an equation like, so this is equation I square RL, we apply the derivative, we get something as V Thevenin square R Thevenin plus RL whole square minus RL into 2 R Thevenin plus RL divided by R Thevenin plus RL whole 4, and this is basically your D power divided with respect to the load resistance. Now in order to have the maximum power, we basically take this power or differentiation of this power and equate it to 0, so that all the power is balanced out. So once we apply this 0 to this equation, so this term is going to be cancelled out, this term is cancelled out, we are left with equation of somewhat of this form: R Thevenin plus RL whole square equals to 2 RL R Thevenin plus RL, and finally RL, the load, has the value of the R Thevenin once you solve the above equation. So this is what we are having. Now the power equation was I square into RL, put the value of RL over here, so we get the final equation to be V Thevenin square divided by 4 RL, and this is the equation we need to use whenever we are asked to find the maximum power transferred to a system or any load. So for example, let us put it into context. Let us say I have this voltage source, any resistor, let's say combination of this, connected to a load resistor. Okay, this is, and these are the terminals A and these are the terminals B. This is, let's say 360 volts, let's say 330 ohm and 150. Now we want to know how much is the maximum power transferred which is coming to this load resistor. So this is the equation that we can utilize, but before utilizing this we need to solve this portion behind the terminals A and B. So we can solve this using the R Thevenin and V Thevenin. How can we solve this? So we can find the V Thevenin of this by considering to be open circuit portion over here. So V Thevenin is going to be whatever is VAB across this portion. So we just apply the voltage divider rule. So we can say 150 multiplied by 360. Sorry, not the voltage divider rule. These resistors are in series. So we need to solve this. So we are applying the R equivalent method. 150 plus 30 over here. So it comes out to be 300 volts. So V Thevenin is 300 volts. And what about finding the R Thevenin? R Thevenin, we can apply the second method where all the independent current sources and voltage sources are turned into zero. So this voltage source will be shorted and we can just apply R Thevenin over here. So again we can see these are resistors just connected in parallel. So we just find the R30 to R150 in parallel. So it comes out to be 25 ohm. So our circuit is that R Thevenin is 25 ohm, and we know that if you want to find the maximum power transfer, we need the value of V Thevenin squared divided by 4 into RL, where RL is nothing but R Thevenin, which we proved from here. So the maximum power comes out to be 300 square divided by 4 into 25, and that is 900 watt. So we know from these analysis that the maximum power transfer from this 360 volt source to this load is around 900 watts. So this is the amount of power consumed by the load, which is R of L. So this is all about maximum power transfer. And the last topic of this chapter from the Nielsen book is on superposition principle or superposition theorem. So it's a very straightforward theorem. It says that if we have a linear circuit, with multiple sources, multiple input sources, so we can find the output, of that source, we can find the output of the source by, or we can find the output, or we normally say the total response of the system by summing the individual inputs, by summing the individual behavior of the sources. So what does that mean? So in this definition, we have to first analyze few things. We talked about a linear circuit. We have already discussed that how we can define any component or circuit element to be linear. So let's say if any element is linear, what are the conditions? So for linearity, we can say, let us say if I have a signal x1 of t and I input it into any arbitrary network, the output I should get is y1 of t. Similarly, let's say I have another system x2 of t and I input into this system, I'll get the output as y of t. Now let us say if I sum these inputs together, these are my multiple input sources. So this is the multiple input sources that we wrote. Let us say if I have x1 of t with any scaling factor plus x2 of t with any scaling factor beta, the output should be the same scaling factor but individually summed together. So x1 will correspond to y1 and x2 will correspond to y2, but they will be added together. So this is basically linearity principle. If you put it into a practical example, let's say if I am talking in a microphone, this is my input signal x1. So this is my voice from the microphone. x2 is some music coming from outside or my surroundings. Now when I input my voice and microphone into the system, the output should also be that you can hear my voice and you should also hear the music coming side by side. So this is what the linearity principle is shown or is explaining through this expression. Now once we have cleared the linear circuits and multiple sources from this definition, let us see how the individual responses of these two sources is going to give us the total response. So for example, let us consider that I have this voltage or this circuit, and let us say it is having these values. So this is a 5 ohm resistor, this is a 2 ohm resistor, and I have another source of 2 amps. So now if you can look in this circuit, you have two sources. One is the current source of 2 amps, another is the voltage source of 10 amps, and I'm interested in finding what is the current through the 5 ohm resistor. So okay, we can apply KVL, KCL, node voltage or mesh currents, but we can also apply the superposition principle that if you want to find the total response, you just take the sum of the individual responses. So how can we do this? Oh, sorry, got it. Total system is sum of total responses, sum of total individual behavior of the sources. Okay, so how can we figure it out? So let us solve this and do this individually. So let us use the deactivation method. Deactivation method, again, deactivation means whenever you have independent sources, you make them zero. So in this scenario, I am going to apply the deactivation, I am going to do the analysis on this first circle, and I am going to deactivate the current source, which means this will become as an open circuit. So my circuit will be now a simple voltage source, 2 ohm resistor connected with a 5 ohm resistor, and then I have nothing over here. So just remove this. So this is 2 ohm, this is 10 voltage. Now let us find the current. Let me call this I1 from this. Why I'm taking this I1? Because this I which we need to find is getting distributed in two regions. So let's say this I which was coming here, it is going as I1, and let us say this is I2. So I'm taking the first loop to figure out individually what is the behavior. So I1 comes out to be V by R, which is 1.42 amps. So I have figured out what is the value of the first current. Okay, this is 1.42 amps. Now let us take the second mesh being this current I2, and I cancel out the first circuit. So now my circuit comes out to be 5 ohm followed by 2 amps, and I have this source, and the voltage source is now made 0. So this is 2 ohm, this is 5 ohm, and now I have this current source. Now how can I find the current I2 across 5? So we know that this 2 and 5 ohm are connected in parallel because they both share the same node, right? So I can say just apply the current division rule. So I2 is going to be equal to 2 into 2 divided by 5 plus 2, which is going to be 0.57 amps. That's it. So the total current I total is going to be the sum of individual currents. So this is the sum of the individual currents. So I1 plus I2, which is 0.57 plus 1.42, it comes out to be 1.99 amps. So this is the current we figured out using the superposition theorem, and that concludes the fourth chapter.